Okay, sir.
Yeah, sir.
Yeah.
Thank you very much
Sir,
for having me.
sir, I will just introduce.
Okay, sir.
Yeah. Very good morning, participants. Welcome to today's session, day 3, session 1. I hope you are getting a handful of information. So today this session is going to be handled by uh, Mr. K. Sudhendra from Bangalore. Sir, please welcome, sir. Before welcoming you, I request our HOD sir to introduce you. I mean, just say welcome. Sir?
Hello, sir. Good morning, sir.
Sir, nice, sir.
Hello, sir. Good morning.
So probably there is a technical issue, sir. Sir is not able to connect with mic. Okay.
Yes, sir. Thank you very much. Thanks for
Yes, sir.
having me.
Please. That's okay.
Yeah, good morning, Surendran.
Sir, good morning, sir. Good morning, sir.
Morning, sir.
Thanks for having me again, sir.
Yes, yes. Thank you very much for sparing your time.
Yes, sir. Thank you very much for giving me an opportunity.
Yes, yes. Please go ahead, sir. Please go ahead, sir. We'll meet
Okay,
you
sir.
at the end.
Thank you, sir.
Right, sir. Thank you.
Yeah, please go ahead, sir. Yeah. Thank you.
Yes, sir. Okay. Thank you very much. Again, I will continue my previous session, whatever I have done on Friday evening in the last session, the recent trends in industry and research in VLSI. But with respect to IoT security, and IoT is just like artificial intelligence, machine learning, and all this. IoT is again another buzzword in last 5-6 years. And let us understand what exactly the IoT and what are the problems in, or what are the research issues in IoT in general, and again in security with respect to IoT security in very particular too. So let us go ahead. Now today's my outline is very simple. What is IoT and how to understand IoT? What are the important components of IoT? Then and again in detail security of IoT with respect to hardware, as with respect not with respect to software, with respect to hardware. The next step. Fine. One thing is, what is the difference between what exactly the difference between 1 minute. Excuse me. One minute, I will restart. I think I opened a wrong PPT or something like that. Yeah. So, what is IoT? Actually, the idea of Internet of Things is to connect a digital and physical world seamlessly to create a network of objects, and communicate with each other. The thing is, the complete IoT ecosystem consists of sensors and actuators, microcontrollers with modest processing and connectivity capabilities, network gateways, and cloud computing. The known challenges in an IoT ecosystem are identification or authentication for addressing an IoT node, choosing a right connectivity technique, maintaining the data compliance across network and security, and basically the core tenets to follow IoT design are agility, scalability, cost, and security. Security is of prime importance because it's a part of a challenge and it is one of the core tenets of IoT design. Let me come back. Let me go back. I have just read out all these textbook definitions, but let us look into the means discourse. What discourse we can have on this concept? So basically, IoTs are new. I can say yes and no. IoTs are, what is the difference between IoT and a traditional embedded system? For example, the desktops, what we are using, desktops and laptops are one type of computers we are using in day-to-day life. And again, we have other type of computers we are using in day-to-day life. For example, a retail weighing machine in a retail shop, a weighing machine in a retail shop, a ticketing machine in the hands of a conductor. Up to some extent, not modern day phones, earlier 5 years or 10 years old mobile phones, and 1 rupee coin phone, 1 rupee coin phone booth. And these are all the basic embedded systems where, or else any simple data acquisition system in a factory, and again all the microcontrollers and all the electronic control systems in a car. All these form a traditional embedded systems. All these form a electronics inside an electronics inside a washing machine, an electronics inside a TV up to some extent. These are all comes under a traditional embedded systems. But how do you differ? You are using a computers in your desktops, and again you are also using a computers in embedded systems. All our embedded systems will have a computer, and our desktop is also a computer. Then what is the difference between the basic embedded system and the desktop is embedded system is meant for a specific purpose, and it will do only that particular job. It will a very defined job. In a desktop, I can install a game and I can uninstall a game, or else I can install a MATLAB, or I can install a Paint, or I will install a Photoshop software. I will uninstall something else. Whatever I want, I can do on a desktop or a laptop. This is a one generic computer. Means we have a generic hardware, generic operating system. It will allow us to install some applications on the operating system. But in embedded system, even though it has, whether it is a operating system supported or non-operating system supported, I cannot install a game. I cannot install a game in a washing machine. I can install the application on a computer used in the washing machine. A washing machine has a computer which is meant for motor control and looking at some parameters, whether water level is sufficient or detergent level is okay or automatic, or a lot of other parameters is there in the washing machine to look after. It will do that particular job. I cannot install any application on a washing machine hardware or washing machine computer. So that is a traditional embedded system. Desktop means it's a generic. I can install applications, and it's a generic computing hardware. But the embedded system is a very particular hardware meant to be used in generally washing machines and consumer electronics, or else other communication equipment. This is meant for embedded system. Then what is the difference between an embedded system and an IoT? From where the IoT came into existence? I think it is the one common question will come always, that what is the difference between IoT and embedded system? 5 years back or 10 years back, they used to call embedded systems. Now they are calling IoT. The same project, same type of concept. 10 years back, someone designed some data acquisition system using a 8051 microcontroller. They connected a ADC. They collected the temperature data and they displayed on LCD, and they said that this is an embedded system product. And now they are saying it is an IoT. Then what is this IoT concept? How the IoT differs from a traditional embedded system? The major difference between IoT and a conventional embedded system is, a basic difference is, IoT is not any hardware what we are doing. IoT consists of the three basic things. One is your embedded hardware. Whatever the embedded systems was there earlier, the same hardware. That is only one component of an Internet of Things. Whatever the microcontroller and whatever the hardware in a data acquisition system, that is the one part of the IoT. Okay. Then again, the next is your internet connectivity. Means for embedded systems, outside world connectivity may not be there at all. The embedded system may not have an external world connectivity. And if it is there also, it may be very specific, like Bluetooth or Zigbee or something like that. It is very specific, or required protocol might be there in the embedded system. But if you want to call it as an IoT or IoT application, internet connectivity is a mandatory thing. Ethernet connectivity is a mandatory thing. If you connect your embedded system application to the internet, then one step is there. One step that is the one area where you are adding up a mandatory internet connectivity to the embedded system, and again you will be using a cloud computing, or else you will be using a mass data storage. Means a large data storage is available for you to store the data which is generated out of your embedded system. So traditional embedded system may have a connectivity or may not have a connectivity, or else if it is having some connectivity, then that may be application specific like Zigbee or Bluetooth, something like that. But in a IoT, your embedded system will be there, your microcontroller, your data acquisition system, whatever the hardware which really connects with the physical world through sensors and actuators will be there. That hardware is connected to cloud through some high-speed internet. A large storage space in the form of the cloud, high-speed internet, and our traditional embedded system. All three components will form the IoT. Which either one of this is missing, means if high-speed connectivity and cloud is disconnected, cloud hardware, that means the cloud storage space and this embedded hardware, microcontroller hardware, which connects to the physical world, both are connected using an high-speed internet. So if that is the case, high-speed internet, if this cloud is missing, then I can call it as a traditional embedded system. If cloud is getting added to the embedded system through an high-speed internet, those things have become Internet of Things application. That's the only difference. The major common man, in the common man's perspective, embedded system is a embedded hardware, a microcontroller which connects to the physical world through sensors and actuators. If I connect that same embedded system hardware, a microcontroller board, to internet, and I will connect it to the cloud through high-speed internet, I have an access to the very large storage space, so that I can save my data. I can save my data generated out of the embedded system. Then the total ecosystem, cloud, internet, the cloud, high-speed internet, and the embedded system is called as IoT. So now what is exactly the difference? Means further, if we go deep technically, generally the most embedded systems are isolated devices without connectivity to internet. In the case of IoT, connection to internet is mandatory. Otherwise, we cannot call it as an internet. We cannot call it as an IoT. Embedded systems will communicate with few devices nearby, and in the case of IoT, billions of heterogeneous devices talk to each other in a ubiquitous network. The thing is, IoT applications are somewhat different. Means the very, very common and again very easy project our 8th semester students or our final year UG students do is the home automation, and I call it as a IoT home automation. And what exactly they do is they connect a sensors to every physical thing in the home, from LPG cylinder, washing machine, tube lights, lighting, TV, everything. They will connect a sensor, and they will connect an internet to every sensor. And again, using a small microcontroller, they will make one particular board which is large enough, little amount of memory that has a server, and they say that this is a complete home automation thing. Yes, that is a small scale IoT, a small IoT cloud a small IoT system, IoT type model is a home automation model, which generally our UG students do. And that's the connectivity is there. Your LPG cylinder, your tube light, your fan, your refrigerator, everything is connected to a internet. And they will talk to the a main server or a main master who gives the instructions what to do and what not to do according to the owner's requirement, according to the customer's requirement. That is one part, that is one small IoT. At the same time, where at least in the home we have 15 to 20 devices connected, like LPG cylinder, refrigerator, light, fan, TV, our mobile phones. Like this, we can list out 15 to 20 connectivities in the home. But when it comes to the very large community-based applications, apart from IoT home automation, which is done by most of the PU undergraduate students in last 2-3 years or 4-5 years, apart from that we have a community-based IoT application. Basically, the three major community-based IoT applications, which is highly explored, and again, a lot of governments, lot of private organizations, and a lot of governments are putting a huge money, including Government of India, is three applications. One is smart city, smart transport, and smart grid. The smart grid, electrical people are working on smart grid majorly, and again smart city, you know what and all happening in the smart city, and again the smart transport. These are the three major IoT based community services where it is IoT's embedded systems connected to the internet, connected to cloud through internet, is changing the way we are living in the form of smart city, smart transport, and smart grid. So in Germany, you can see every house is a producer of electricity. On the terrace of every building, you will have a solar plates generating electricity, and again everybody contributes some electricity to the grid. And again, at the end of the month, how many units you contributed and how many units you consumed from the grid, the total that will balance amount, either you will pay if you have used more number of units, you will pay, or else that power supply company will pay you back if you have contributed more units, and again if you have consumed less units. For the difference, they will pay you back. Electricity company will pay you back when you have a surplus units. When you have a surplus units, and again it means the customer has to pay when he has more units. So this is all possible in a smart grid application. At the same time, for a car, exactly for a car, right? For an automotive car, for example, till now, at least from last 30 years, 35 years, we are seeing microcontrollers in every car, almost in every automotive bus, car, or whatever it is. We have a lot of microcontrollers getting in. The number is increasing every day, means every year. Means I have an engine management system, which is again microcontroller driven. I have a power transmission, which is a microcontroller driven, which is a safety devices like seat belt, airbag, and all, which are all microcontroller driven. And again, I have a power windows, all are microcontroller driven. Heating, ventilation, and air conditioning is again microcontroller driving. Lighting, again microcontroller driven in the car. At least by 2006, to the best of my knowledge, we had around 80-85 microcontrollers, or 60 to 80 microcontrollers in a car, and that is 15 years back. I think now it has been increased a little bit, or it was sustained. 80 microcontrollers in a car is a huge number. So earlier, 15 years back, there was no high-speed internet, and every microcontroller used to, the embedded system inside a car used to be an isolated system. Now, if I make them an IoT, if I convert them into an IoT, what happens? Means now power transmission is there. Then let us take three crucial things in the car. One is a engine management system. Another one is a power transmission. Another one is a safety. All three things, all the three systems will have a lot of sensors. Let us assume that all three things are connected to internet, and we have converted an embedded system into an IoT. Data center is the vendor data system. The company, let's take Maruti Suzuki or some Hyundai or some company from where I have bought a car, he is maintaining a data center. Once I purchase a car from a company, they will connect my car to their data center. Every 15 minutes, they will collect the data from my car. Every 15 minutes, they are collecting data from my car. What is happening in the car? Okay. or else if the car is running, then it will start everything. So they will take the data from the car when the car is getting operated. When that is the case, if they get any discrepancy in the data, means if the slowly some repair required, or some mistake is happening, some problem is there inside the car, still I am driving, the car has not stopped malfunctioning to the user, but inside in engine something is getting developed, or in the transmission some mistake or some error is getting developed, so sensors are giving a wrong data. Then in the people in the data center will be monitoring the data. There the people will get this particular car traveling in this place. It's traveling in Rajam, Srikakulam. And again that particular car is developing some problem. Immediately from the data center they will call you and they will tell in next 20 minutes your car will break down. Our engineers are nearby, they will reach you within half an hour or 1 hour, and they will repair the car, but don't drive the car, you stay where you are, our engineers are reaching you and they will repair the car. You don't know in next 15 minutes or in half an hour my car will break down, we don't know, but the data center knows, because data center is collecting a data from a car. Data center is collecting a data from a car, and again they will call me back, and again they will say that in next 15 minutes or 20 minutes your car will break down. You stay where you are, our engineers are coming and they will repair it. So this is how I don't know whether my car will break down. I don't know. In next 15 minutes, car will break down. But the data center knows, because they are collecting the data from the car. And again, another usage is they are collecting a data for 1 year, means for 3 years or 5 years, whatever the warranty period is, that they will collect the data. After collecting the data, every year I can ask for the car data. For this particular year, from this month to this month, give my car data. From January to December 2019 data, I will take a car data. By looking at that car data, I will bargain the insurance premium with the company. Look at my car health. My car is very healthy. Why should I pay high premium insurance? Reduce the premium. If car is doing really bad, if the car parameters, whatever the basic car parameters are there from the car systems, engine management, power transmission, if the parameters are really bad, then insurance company may demand a higher premium. And again, at the same time, the user can also bargain with the insurance company that, see the car data which is collected for 1 year, my car is very healthy, why I should pay a higher premium? So give me the less premium. I can go for a less premium, and this is where exactly the usage of IoT is there. Usage of IoT is there. IoT is there. So the usage of IoT is there. So this is where exactly how embedded systems are getting transformed to IoTs. Now the embedded systems, whatever the products and services we have in the form of embedded systems, they are getting the high-speed internet. They are connected with high-speed internet and the cloud. They collect the data, and again the data is used for different purposes, different applications. This forms how most of our application verticals, it may be an automotive, consumer electronics, communication and networking, medical electronics, military and aerospace, everyone, whatever the embedded systems are there, they are trying to convert it into Internet of Things. Another difference between the IoT and the conventional embedded systems is the amount of data getting processed. In IoT ecosystem, large scale data compared to the embedded system. IoT ecosystems processes a very large scale data when compared to the traditional embedded system. So this is one part, how exactly the traditional embedded systems and IoTs are different. IoTs handle large amount of data. Then next, another thing is IoTs and cyber physical systems. Then the CPS is not a very new thing. It's a very old thing. So very old means how much old? From last 50 years we are seeing CPS. In 1960s, 1970s, most of the factories started getting automated. And again, the cyber physical systems which comprises of both cyber and physical world. Basically, the CPS is an integration of sensors, actuators, communication networks, and control systems in which status of a physical system is monitored. The system is monitored with the help of sensors and suitable control action is taken. The concept of IoT is very similar to CPS. The CPS is very established domain which has got a numerous applications similar to IoT like smart grid, etc. Basically, the factory automation, any process control, it may be any bottling plant or it may be petroleum processing, chemical processing, and any factory automation, any manufacturing system use CPS, cyber physical systems, for better productivity and all. So the cyber physical systems do exist from very long time. But how the CPS and IoT differs? Because as far the functionality is concerned, structure is concerned, the CPS and IoT are same. Because IoT and CPS both have a sensors and actuators, communication network, and a control system. But how does the IoT differs from the CPS? How the IoT differs from the CPS is, only thing is communication link is a different, amount of data getting generated is a different. Here in IoT, the communication link between the nodes is mandatorily internet. But in CPS, can use only a limited scope will be there for the connectivity. If it is a factory automation, it is limited to its factory. And again, if it is some supply chain management, then again, the CPS concepts are very limited to that. Or else it is something like that, it is very deterministic to the organization. It is very limited to the organization. And again, its scope is very less, CPS scope. But the concept is same. The CPS and IoT theory is same. But where exactly they differ is through a internet. The communication link in the IoT is internet. In CPS, it can be CAN bus, mode bus, Profibus, any type of a system bus. And again, the number of systems connected to the communication link in IoT is very huge. It can go up to the billions. In the case of smart city and smart grid, smart city and smart grid, But in the case of CPS, it is very limited. In the case of a CPS, it is very, very limited. So then basically the CPS is a system infrastructure and IoT is a networking infrastructure. IoT is a networking infrastructure connected to a large number of devices compared to the CPS. In the case of a CPS, the real-time control is a primary goal. If for a CPS, real-time control is a primary goal, while in IoT, real-time control is not a primary goal. Resource sharing, data sharing, effective data crunching with minimum latency are important. Effective data crunching with minimum latency are very important. I cannot have a avionics connected to the internet. I cannot have a missile control system. Means in missile control system, it's a real-time control. Latencies are very specific. The latency should be very specific. So I cannot have even a 1 millisecond latency in a missile control system. I cannot make a missile control system into IoT. It's a baseless and it's a foolish thing. I cannot have a avionics hardware connected to the internet, not required. So if aeroplane is flying somewhere in the high skies, what is the use of an internet there? Means connecting the internet is not possible and it is useless. So whenever there is a real-time control means the latencies are stringent. Missing a 1 nanosecond, or sorry, missing a 1 microsecond, missing of 1 microsecond latency means if the data comes 1 microseconds late, the system may crash. Aeroplane may crash, a missile may hit a wrong target, anything can happen. So in the where we have a real-time constraints, IoT does not fit the purpose, because the internet speeds, internet connectivity are not much reliable. So there may be a question. So there may be one example which generally people tell. There may be an operation, a cardiac surgery or some operation, some surgery happening in India, but doctor is sitting in America and he is operating from the US through robots, and he is performing an operation through robots in India using an internet. The people are doing operations. Yes, no doubt, operations are also getting success. So this is more than real time. It's a life is at stake. Life is at stake, and the internet is working. Why can't we call IoT for also for the real time control? But here, in the case of a doctors, the one expert doctor is sitting in US. There are other 4 or 5 doctors surrounding the patients to take care if internet fails. There is a backup not only through the robots he is controlling. There is a continuous communication between the doctor sitting in the US and the 4 or 5 expert doctors surrounding the patient in India. So that is a very exceptional case. That surgery example is a very exceptional case where embedded systems can be converted in all, even the CPS, even avionics, even visual control systems can be connected, can be operated through internet. Is that particular example is a very exceptional case where they have other alternatives also. If the internet fails, there is other alternatives. Alternatives are there. But in the case of a missile control system, or in the case of avionics, especially in the case of avionics, there is nothing alternative there. There is nothing alternative. So whenever the real-time controls comes, when there is a real-time requirement comes, IoTs may not fit in every application. IoT is meant for resource sharing, data sharing, effective data crunching with time effectively, cost effectively, with minimum possible latency, with no hard real-time constraints, all real-time constraints. But CPS is real-time. The CPS must be real-time. Otherwise, in a factory of a petroleum processing or in a chemical processing industry, if the real-time control is not there, then the reactions will be different. That may lead to an accidents in the factory. Anything can happen. The CPS is generally designed for real-time control is a primary goal, but in IoT it's a different. Basically it's a data. Where we are generating a lot of data, there IoT is required. Where this is not a real-time control is not there, then IoT can be, that type of embedded systems can be converted into IoT. Now, I think we have discussed about the traditional embedded systems, difference between IoT and the traditional embedded systems, and IoT and the cyber physical systems. Now next, then other part is security aspect in CPS is much simpler challenge than security of IoT, because number of equipments we are handling, the number of process nodes we are handling in CPS is limited, maybe 16, 32 or 48 or something like that, which much less. But in the case of IoT, we have a millions of devices may get connected, or as hundreds, thousands is very common in the case of an IoT. At least in the home automation itself, sometimes it goes above 30. At least in a small home, the nodes may go up more than 30 in the case of home automation IoT product itself, because we will have at least 15 to 20 lights itself. 15 to 20 lights, refrigerator, fans in all places, easily go above 30. So in a small home automation, if we have a 30 processing nodes, we can imagine in smart city how much it can have, and smart grid, the nodes will go up to the billions. Then again, for the security, cryptography, applying a cryptographic techniques in CPS is enough, but we need a different type of security in the case of a IoT. So this is the basic differences. What is IoT? How the IoT differs from embedded system, and how the IoT differs from cyber physical systems has been discussed. Now, what are the factors? Why now? Why in last 5 years the people talk about IoT? Why not in 2010 people didn't speak of IoT? Why not in 2005 IoT concept didn't come into exist? Why now in 2020 or 2015 onwards, why people are talking about IoT and why IoT is a buzzword? That's it. The three reasons which most of the people will agree is, one is relatively availability of the high performance processors at very low prices. Means availability of processors at very low prices means, take a case of ARM processor. Why ARM? Why we speak about the ARM is, just like in desktop market, Intel is a very dominant player. The desktop, laptop, servers, we have in Intel processors. At the same time, in the embedded world, whether it may be a small scale embedded application like coin phone or anything like that. At the same time, a mobile phone, which is a very complicated embedded system as of today, in all the places we have a ARM processor. Just like a Intel processors are the widely used and again benchmark for desktops and laptops, ARM is another benchmark for embedded system market. So I am talking about the ARM processor. Generally, from the day one, or else from the very early days of inception, ARM is produces a very high performance processor because they started with a RISC mission in 1986 and they produced relatively high performance processors for embedded systems. So ARM controllers were not cheap. ARM controllers were not cheap. Even till 2005, 2006, or even up to 2010, the cost of ARM processors was very high, relatively very high. But after 2010, gradually, for various reasons, for cost control, competition, market trends, for various reasons, the prices of these processors came down drastically. The prices of these ARM-based microcontrollers prices came down very drastically. So that, for example, if you want to purchase a ARM processor in 2004, it would have costed you 300 to 800 rupees. Now you can get an ARM processor at 60, 70 rupees per piece. So there is a drastic reduction in the prices of a processor which is really high performance like ARM. Not only ARM, there are a lot of other high performance processors for which the cost has been reduced drastically. So availability of high performance processors. The next one is a cloud. In the form of a cloud computing, we have a infinite amount of memory availability. Memory is available. I am not worried about the memory. I can connect it to the cloud. I can connect to cloud. Whatever I want to save the data, all data I will save. So there is no cloud computing, storage technologies in the form of a cloud is another thing which is helpful for the advent of IoT. And the third and most important thing is connection between this embedded system and the cloud was established through wireless communication system, read 4G, to connect the multiple layers in the system hierarchy at affordable prices. I think we can imagine, right, how much we are using, the amount of internet we are using in 2010 and 2020. Right? The 4G revolution and 5G is coming, the high-speed internet. These three systems are affordable prices for high-performance processors, means enormous amount of data storage capabilities in the form of cloud and the high-speed internet. All three as all the factors responsible for the emergence of IoT. Earlier, IoTs were there, but they are isolated things, and we called them embedded systems. Now we call most of the embedded systems as IoTs because high-speed internet is getting connected to them, and again we have a cloud for storing the data. So all these factors made a concept of IoT into reality, which is redefining the product and service in most of the application verticals of semiconductor, as we have discussed earlier. The next, what are the research problems in IoT? Means basic research problems in IoT. I am not going very deep. I am just naming them here. If I am building an IoT, the basic things is generally millions or billions of devices generate a disparate data with their own formats. So data transmitted from one node to gateway and to the cloud should use a same data format which should be understood across the different IoT layers. So there is no compliance, data compliance, because one node will generate the data in a different format and another node generate the data in a different format. So this must be handled. There must be some standard which is still not yet worked out. The people are working, and again, many companies they have their own data compliance standards for IoT products, but a common a community-based data interoperability or data compliance is not there, where EC people have a very less role to play. Reasonably, we can play a role. Still, the computer science people will take care of this data interoperability, data compliances, and all. The next one is most of our IoT edge nodes, I will call it as an edge nodes, that is our embedded systems, traditional embedded systems which which interface with the physical world, they are all battery operated. Because I cannot have a power supply connected, a main line connected to them always. For example, if I am monitoring a in a smart city project, if I am monitoring the quality of a water in a lake, quality of water in a lake. So I will install some sensors in the middle of a lake, in the edges of a lake, or at appropriate places in the lake. I will install the sensors and actuators with a microcontroller connected with an internet. The microcontroller will collect data from sensors, put that data in the right format, and transmit it to the server, transmit it to the cloud through high-speed internet. Most of the IoT edge devices are low power and battery operated. Obviously, a node which is installed in the middle of a lake to monitor the water quality is battery operated. Is a battery operated. Choosing components, so we have to choose a right microcontroller which really gives me the low power, which really gives the low power. So choosing the components to design an edge node is very important. The microcontroller or a SOC used in the edge device, a microcontroller or a SOC used in the edge device. IoT edge node means the node, the edge layer or the edge node or perception layer. A lot of names are there. Edge node, edge device, perception layer, edge layer, whatever we can call. All this edge device must support internet connectivity. And internet connection is not optimized for low power consumption. Whenever you connect the internet to them, there will be a lot of battery getting drained out due to the internet connection is very high because of switching activity is very high in the internet connection. So this is one of the challenge we have. So how do you design a microcontroller for IoT edge node? How do you ensure that another problem which the industry didn't, even industry and researchers didn't think in all these years is low power internet. Low power WAN is there. Low power wireless area network or something the people are thinking out, but it is not yet optimized. Somebody can think of a low power internet, or else another area is what can we reduce the total? Can we design a very application specific IoT processors itself? For example, why I need a 8-bit microcontroller, with complete instruction set for IoT. For a IoT itself, IoT processor design itself is another new area where IoT microcontroller design itself is a very new area of research. We cannot do IoT microcontroller in PhD research, but we can choose either low power internet or else low power microprocessor design in the area. So because as the internet connection is not optimized for low power, designing a hardware, designing an edge layer, both at VLSI level and both at embedded system level or device driver development, choosing a right device, everything is challenging. Otherwise, every another day, you have to go in a boat to the middle of a lake, then remove the node, put a new battery and come back, which is very difficult it's a difficult maintenance, difficult to maintain that. So the power management in IoT devices is crucial. So it should be powered on and connected to the internet continuously. Generally, these applications are data intensive or data specific. So data is important. Means the pollution control board stringently say that every half an hour I need a data of the quality of a lake. I need a data for the lake quality, water quality in the lake. So we have to go by compliances. So the device cannot shut down. So the low power is very important in IoT. Means low power, and in this case, what happens is low power was only a problem of VLSI engineers, really. But with the advent of IoT, now low power software, low power device driver development, low power software engineering, everything has got very important. That given a hardware, okay, at the device level, the VLSI engineer, what he can do, he has done to make it low power. That is, he has done low power microprocessor, low power Ethernet, low power interfaces and all. But it's now part of an embedded software engineer that how we develop a low power software, how we develop a low power device driver with a minimum switching activity so that battery is protected. So that battery I can use for one more extra day. is one of the challenge in the low power engineering. The designing an edge node with a low power component without affecting the performance is a challenge. Means the performance is also equally important. May not be a real-time constraint, but it's equally important, the performance also. This is a compromise somewhere we have to make. The next is what are the basic research problems in IoT? Whatever the basic research problems in IoT, apart from data compliance and the low power, another one is the security and privacy. Either in CPS, cyber physical system, or in the traditional embedded system, our basic, if any security is required, that was basically a data security. Data must be protected from the adversaries. Some important data from some confidential data do exist in the system, so we have to protect it. So you just encrypt the data while sending it outside through any bus. If you are sending it through any bus, just pass this data after you encrypt it. At the receiving node, you decrypt it, so no problem. The data security and privacy was achieved through using implementing a one cryptographic software. Cryptographic implementation was enough. But in this case of IoT, either only cryptography is enough, yes and no. Yes and no. Because in the cyber physical systems or in a traditional embedded system, the number of nodes or number of nodes was very less. The number of nodes and number of people were very less, and again the data management or connectivity management was easy. But in this case of IoT, there are millions of nodes. At least not millions, at least we can have thousands of nodes in practically. So that when thousands of nodes are connected in a network, there is a lot of security problems. Then it created as that IoT security has become a multidimensional research problem. The product development and manufacturing are highly diversified in the IoT ecosystem. The reason is the product development and services in IoT. If it is a traditional embedded system, there is no much problem basically. Okay, if I want to develop an engine management system, or let's take a home automation product itself. Home automation product, I will buy a microcontroller board, or else I will buy microcontrollers, I will develop my own board, I will write my software, and I will go and sell it, no problem. But here, if you make it a home automation as an IoT product, you need an internet connectivity. Then you have to depend on service providers like Jio, Airtel and all, number one. Another one is you need a cloud. If you need a cloud, then you have to talk to the Google, Microsoft or Amazon, who are the cloud service providers for the common man. Then if you are making a product with IoT, then you have to coordinate all three people: cloud service provider, internet service provider, then you have developed your hardware in compliance with their requirements also. It's not the customer requirement is one part. That means the functionality of a product or the customer requirement is a one part in product development of the IoT. And again, you have other two parties involved. One is the internet service provider, another one is a cloud service provider. You have to bring for your given product, you are the interface to the customer, then you have to ensure that their connectivity and the cloud service also should work for your customer. Means it's something like basically it looks like a management problem or a managerial problem. But basically in hardware, in designing the hardware itself, we need to think in a different way that can we switch the internet service provider without any lot of harassment? Can we switch different clouds? Can the reliability of a system can be improved? I mean, this lot of engineering research is required. If you are going for the product development and manufacturing for IoTs, it's not easy because the edge device we may develop, a physical interface we may develop for sensors and actuators, which is relatively independent. But when it comes to the high-speed internet connectivity and the cloud service provider, it's not in our hands. We have to ensure that if we want to ensure reliability for our customers in our products and solutions, in IoT-based products and solutions, we have to be innovative that switching between the internet service provider and switching between the cloud service providers must be easy and without much harassment. So the lack of standards in edge device development and the gateway design. Basically, the gateway design. It's not only the internet. At the end of the day, the gateway to the cloud is internet. Then how do you interface the edge node and the cloud? This is again another lot of research going on. But at the end of the day, each IoT node will put the data into the internet gateway. Then that will carry it away to the cloud through high-speed internet. But this in microcontroller fellow who is sitting in the edge, he has to collect the data from the gateways different gateways. One sensor is connected through Bluetooth, another website is connected through something else, another sensor is connected through Zigbee, another sensor is connected in a wireline through ADC. So like this, there is a lot of things. He has to connect one Bluetooth, one Zigbee, another low speed internet, something like that. He has a lot of the edge device development has become a very challenging thing. At the same time, we have to achieve a low power supporting all ad hoc communication systems, and also where exactly the products and solutions development of IoT based, it's not very easy. Only a large scale people can do, where car manufacturers, smart cities, smart grid, smart transport, where large scale investment, where they can maintain their own cloud, they are relatively successful as of today. And when it comes to the small scale thing, where we are incorporating, where we are including the third party cloud service providers and the third party internet service providers, IoT products and solutions are really struggling to meet the customer requirements and reliability problems. So this is where exactly we can think in hardware and software to solve these problems. And more details can be available in the literature related to the IoT product development and manufacturing and this one. And there are no lack of standards in edge device development, and the gateway design will create a compatibility issues across IoT edge nodes in the future. This already it has become a too much problem here. Then again, there is a need for regulations and standards to follow in designing the edge node and gateways. Developing standards for and regulatory mechanisms needs a serious research. What exactly we do looks like a management problem, but only the engineers can solve what should be the regulations and standards in the IoT edge device development, and what is the regulations for internet connectivity, and how the cloud service provider should be more reliable. Everything is needs to be worked out, which is not mentioned much in the literature. We can see the IoT journal, IEEE journal of IoT. Every issue we can see a lot of discussion happening about this regulations, developing standards. We can see the at least Government of India Sri Krishna Commission on Data Security or Data Management when it comes to the IoT products. Justice Sri Krishna Commission is there. You can see the report. You can see the report once, and again we can understand what are exactly the problems pertaining to this particular area of product development and manufacturing. Another thing where exactly is the problem lies is, if I am giving a solution to the IoT smart city or IoT smart grid or IoT smart transport, the data generated by the IoT node, it belongs to whom? Whether, for example, if it is a smart city project, the data belongs to whom? The data should belongs to a local municipality. That's the sensible thing. But the guy who have developed the IoT products, he will say the data belongs to me also, because it's my device collecting the data. That's where exactly the regulations and standards required here. Okay, the next case is, another one is analytics. Data mining and crunching is a crucial component in IoT system. We have a lot of data getting generated and a lot of things getting stored in the cloud. So then how to manage with this? How to manage with this? We have to manage the analytics. How much computing we can do? Distributed signal processing, you might be knowing. How much signal processing can be done in wireless sensor nodes, and all was a very old problem, 10, 15 years old problem. Wireless sensor networks and DSP, how much DSP they can do in each node. This is all very well discussed research problem. It's relatively same problem. how much data. If it is a very large amount of data, I will crunch or I will compile the statistics. I will do all my statistics. I will run all my statistical algorithms in the cloud. I will run the statistical algorithms in the cloud. So that is one part which is very straightforward, and most of the companies are doing today. But when it comes to the performance improvement and all, why I cannot do some amount of data crunching or data management in the local edge node itself? If I have a bandwidth, and again if I have a very high performance processor like R, why I cannot do data mining and crunching in the edge node itself? That's the one area which the people are looking into. How much of data crunching, data analytics can be done in the edge node is a question mark. Then handling a different patterns of data is a unique challenge in IoT, which we have already discussed. Apart from cloud computing, in modern day, in the recent days, we are listening a lot of other computing concepts like fog computing, mist computing, and all. The amount of computing we can do in the IoT edge nodes can be called as a fog computing in a very in a raw way. The raw definition of fog computing is the amount of computing what we can do at the edge node can be called as a fog. And again, the mist computing is where exactly is the somewhere all nodes clubbing together, they will do some computing in the gateways. That is something called as a mist computing. Even I cannot have a clear and proper definition for a fog computing, mist computing, and other dew computing. We don't know cloud computing, fog computing, mist computing, dew computing. We don't know actually what every researcher defines as new model, and again they come up with a new concept in IoT, basically on the different computing models. We have to work out, we have to look into which fits into my products and solutions, and there's a lot of scope for research here actually. The fog computing, how much data crunching I can do in the fog computing model, how much data crunching I can do, and how much performance I can achieve in the mist computing model. Then what is this dew computing really, how it differs from mist and fog, we don't know. The traditional data mining algorithms suitable for centralized computing infrastructure does not fit into IoT. Everything I will do in the cloud, it will jam the cloud, it will create the traffic jams in the cloud. And again, we have to pay more for that if we put more data into the cloud for the cloud service provider. So this is exactly the fog, mist, dew will come into the picture. There is a need to develop a novel algorithms for data analytics which can support fog computing, mist computing, dew computing in the modern IoT requirement. So you have to find out a model, and you have to redesign your process, redesign your memory interfaces in such a way that they support all these requirements like fog computing and mist computing, etc. The next is another one, factors affecting the security of IoT. Very particular, till now we have discussed the research problems grossly, very overview of a IoT research problems, and pertaining to what VLSI engineers can do for IoT and its betterment, and what embedded software engineers can do for IoT and its betterment, we have discussed. But now let us very particular to look into the security, because security is always a secondary concern. Most of our design engineers will look for the functionality. The functionality is a prime concern. And again, secure and cost of design, cost of production, how much better functionality we can design. This is basically the primary concerns of a designer. But security is always a secondary concern. Generally, in our electronics or any product development, security is a secondary concern. But in IoT security must be a primary concern. Otherwise, it's vulnerable. It's our organization may be vulnerable. Our customer is vulnerable. A lot of problems will be there. The first factors affecting the security of IoT is the scalability. The major challenge of security is scale, diversity, and customization. The IoT system will have billions of devices connected in the internet. Designing an holistic data and system security using generic cryptographic techniques for a large system is difficult. So we need some networked security. We have to work out which hardware we should use. In the last session, I said about lightweight cryptography. In the lightweight cryptography, how much we can use? Choosing which lightweight will work for me is a basic challenge. Choosing a lightweight cryptography, it may be a Simon, Spec, Present, Rudra, any hardware, any cryptographic hardware or cryptographic software implementation, choosing for IoT is a difficult, whether it's scalable or because of number of nodes. The next one is diversity. Diversity means it's one is a some sensors hardware is different, the data formats are different. These are all the issues in the diversity is another problem. Next one is device life. In IoT applications, device life is very short. And in few applications like automotive device, life is very high. Security techniques needs to be designed based on the application and device shelf life. A car will be used for 8 years, 10 years, 12 years, sometimes 20 years. So the device life there is very high. But in the case of a mobile phone's device life is not more than 3 years or 4 years. So like this, the sometimes device life is short and device life is long. So the security techniques needs to be designed based on the application and device shelf life. For the devices with the long life, there must be an option to update the security features through software or firmware updates to defend the new threats and attacks. The very short life is okay, but when it is for a long life, there must be a scope for firmware updates for a defend against the new threats and attacks. The next is most of our IoT will use a open source softwares. The classical example is our students doing projects in the UG level or even in a PG level. The thing is, they get the Arduino board, they get some open so already available code in the internet. They will dump it and they will check out. Then they will tell that it is working. But who will guarantee the reliability and safety of that particular open source code? Open source code. And again, this is very important. Developers should carefully choose the software and must have a framework to validate the open source software. It does not contain any malicious functionality and all. Then there is another very important thing is over the year a firmware update or upgradation for the IoT systems. For IoT systems. IoT systems can be upgraded remotely through the network. Means earlier days, if it is a software update, you have to go to the customer place, remove the hardware, connect it to the JTAG, and dump the new firmware and all. Now, why we cannot do it through internet? If it is a IoT node is installed in the middle of a lake or inside a substation where I cannot go frequently, through internet I should able to upgrade the software. And again, this becomes a threat. This becomes a threat because they will hack the internet, he will hack our network, and he will install his own firmware onto the edge device, and he will crack the total net, he will leak the confidential data, anything can happen. So online software update in IoT edge nodes or IoTs must be carefully designed so that no adversary can break the internet and do the malicious software or firmware upgradation. So the proper authentication and identification of an edge device in the network of billions of devices, and to make sure that no malicious drivers or software is not installed on the edge devices in the name of updates and upgrades must be taken care. Otherwise, we will lose out. Then next, the cloud data center. All commercial activity in the IoT is supported with a cloud-based data storage infrastructure. The cloud is an integral part of IoT ecosystem and enables most of the services. The cloud security and IoT edge device security are mutually dependent factors. How do you ensure that it's an holistic system? The cloud is not damaged due to the IoT, and IoT is not damaged due to the cloud. Because the IoT edge is, for example, IoT edge node, for example, if it is a Raja municipality, install some smart city project, they have an access to edge node. They can do, their service engineers can do some IoT edge node. They can monitor the IoT edge node in the middle of a lake or in the main road, in the main road where air pollution is monitored, and everything they can do. But they are sending the data to the cloud. If any threat or attack comes from the cloud side to the edge node, then the people who are having the custodian of edge node cannot do anything. But at the same time, through edge node, if somebody attacks the cloud, that is also possible. So the cloud security and the edge device security are mutually dependent factors. So the cloud service provider and the IoT edge node user should coordinate so that from each other there is no security threat. They have a security systems in the place where our security designers, software designers, and hardware designers should look into holistically so that this cloud data center and IoT edge node security is holistically designed and comprehensively addressed. The next is authentication and pairing. A large number of devices in the IoT network complicates the pairing of devices. A pairing is required to aggregate and segregate the data generated from the edge nodes. It is important to make pairing process secure. The adversary can tamper with data and node identification credentials. Compromise in the security at one node may open up communication channel among device to device and device to routers. And power consumption and security are closely interconnected in the IoT. So, security architects must consider power consumption patterns and available power supply capacity at the edge node in designing the production of the edge nodes. I can design a best security, I can design a hardware which is highly secure, but power consumption problem is not addressed. And I will develop an embedded software which is highly secure, but power consumption pattern is not studied. So in security design, we have to take care that power, it should not drain out the battery. My security software, my cryptographic algorithm should not drain out the battery in the edge node. It has to be a low power security algorithm. It has to be low power security algorithm. It has to be low power security hardware. It has to be low power security software. So that is where exactly the challenge is. This is one of the challenge in the designing a low power secure system is a challenge in IoT. Is a challenge in IoT. The next is
Hello. Hello.
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Yes, sir. I'm continuing.
Yeah.
So, what are the known attacks on the edge node? What are the known attacks on the edge node? The known attacks on the edge node are like this: node capture attacks, a malicious code injection attack, false data injection attack. These are the attacks which are well known in the IoT edge layer or IoT perception. An adversary will capture the node or replace the entire node or tamper the hardware device to leak the confidential information like keys and digital right management. Or else you will install the malicious code on the edge node and you will compromise the total security of the network itself. So these are the known nodes. These are the actually any problem in one node means if it has any issue with one particular node, we have to kill that node, disconnect. We have to immediately disconnect it, or it automatically the security system should disconnect it. Something we have to take care. But that cannot be done at only through software. We need hardware support also. There is a sleep deprivation attacks like a denial of service by draining out the battery, like the tampering the hardware or pumping the malicious code into the memory. That is, the code executes in an infinite loop can increase the power consumption of the edge device, which leads to the draining out of battery and creating a denial of service type attack. The another area is booting vulnerabilities. The basic problem is overall my security is fine, excellent, but during booting process, while the system is booting, I don't have any. After the system boots, then operating system will boot. My first board support packages will boot. Then next, after the board support package boots, then operating system will boot. After operating system boots, all my applications will start booting. So generally, all our security-related software applications will install are at the application level. We are installing antivirus as just like a MATLAB. On our desktops, we are installing antivirus software as a MATLAB, as an application. But if anything happens at the operating system level, or if anything happens at the board support package or a device driver level, These vulnerabilities are always there even for our laptops and desktops. But that is in our physical possession. Our laptop or desktop is in our physical possession. We can take care of it. But in the case of IoT, if I am putting one IoT edge node in the middle of the forest, where I don't have a physical access always, some adversary will go, he will disturb the booting process, because that security are all operating system level and application level security procedures are there. He will disturb the booting process. During the booting, he will enter into the hardware, and again, or else he will enter into the memory, or else he will enter into the network, and he will compromise the security, that he can leak the secret keys, and secret keys used in the encryption and all other IP rights can be compromised. So to address, even during booting, we should have some security mechanisms at the device driver level. Even at the hardware level, we need some security security component included in the hardware. And again, during booting, some security must be there, so that no data will be leaked out. So in the next case is, adversary can access the debug ports like JTAG and access to the on-chip instruments used for debug and diagnosis to get an access to confidential assets of an edge device, which are commercially sensitive. IoT designers should choose a microcontroller with a suitable debug security features, or designer has to create a protection using a security firmware. The problem for an IoT designer is a two-pronged. One is for a researcher in a university. If he is a VLSI engineer, he has to think of creating a comprehensive IoT security block. For example, there is a clock managers in FPGA, or the clock management in high-end microcontrollers, in 32-bit microcontrollers. We have a clock management system. And again, we have a power management system. The same way, we need a security management system in the modern day microcontrollers. And there are very few microcontrollers from very few people. It is available, like Unlock Devices and Freescale, and from Texas Instruments. They have a minimum security feature for very specific things. But there is no holistic security features. Holistically, it is not addressed. So another one is software exploitation, is very similar to the software related bugs. And again, this is same applicable. All software related bugs, vulnerabilities are applicable to IoTs also. So here the basic, looking at this IoT edge node vulnerabilities, we can identify the two tracks here, the two parallel tracks here. One for VLSI engineer, another for embedded software engineer. One for IoT, for VLSI engineer should look into both security and power and new architectures. Somebody has to design a new architectures for IoT processor and IoT security blocks in the similar lines of clock managers and power managers, power management units, and that is voltage regulators, or else clock management units like DCMs in FPGAs, what we are using from Xilinx. In the same way, somebody has to design a security block inside a microcontroller that should address all the, not only the specific particular security vulnerabilities. Overall, it should look into the holistically all IoT edge node requirements. Number one. Number two, embedded software engineer should use that security block developed by a VLSI engineer, and he should think of developing an effective usage of that security block to develop this one. This is exactly, we can say, the hardware, the engineer who is looking into the IoT system can clearly break up what should go into the hardware and what should go into the software. And again, there must be a modular system, which must be a programmable security block, inside the microcontroller, so that it will enable the embedded software engineers to develop a required efficient security software, low power software. And again, it must be a low power hardware also, a low power security hardware and low power security software, which addresses the holistically, comprehensively all the vulnerabilities what we have discussed till now. So that is actually a research problem. And again, industry is working very hard. There is a lot of academic research happening in this direction to develop a low power security hardware inside the microcontrollers, a VLSI problem, and again low power security firmware, which is an embedded systems engineers or software engineers problem, which is going on from last 3-4 years. The recent advancements, there is a lot of advancements at the network layer, at the software layer, at the gate level, but at the firmware and at the IoT and at the VLSI level, at the hardware level, the reasonably a less amount of work is done. If somebody interested in doing research can take up, look into this ideas grossly. At least in this presentation, I have not gone through the details. I am just presenting grossly a bird view of IoT security and how to make it. The challenge is how to make it low power and how to make it holistic. It will address all forms of problems. So this is the one research problem we have. Then what are the existing solutions? I'm asking, does anyone has done anything? Yes, the people have done a lot of things. Like there is something called as a TEE. TEE means Trusted Execution Environment. The trusted execution environments are both that some part of hardware will support, some part of hardware will be there, and some part of software the people has to develop to security solutions, especially such commercial problems. The commercial solutions are like ARM Trust Zone, Intel Software Guard Extension, Samsung Knox, and these are the basic three things which are very widely used. Samsung Knox is in our mobile phones. Intel Guard extensions are there in our FPGAs. That is Intel FPGAs. ARM Trust Zone is there in every ARM controller what we are using in our day-to-day applications. But how much we are using them, whether they are efficient, what are the advantages and disadvantages of these three commercial security mechanisms, TEs, that is trusted execution environments. We have to look into a literature for that. We have to look into the literature for that. So we have to deep literature for that. So then again we can develop our own. We may not develop a complete ARM Trust Zone or else Intel software guard extension. If you want to read about the Intel SGX, you can read one MIT paper which is around 110 pages by Srinivas Devdas and his student. There is a very good explanation on Intel software guard extension, how they are developing, what we can do in hardware and what we can do in software. ARM Trust Zone is also very widely used and widely discussed in security of IoTs, especially both hardware level and software level. Now the problem is, inspired by the ARM Trust Zone or the Samsung Knox, can we develop an open source security solution, open source security hardware, which addresses the IoT security holistically, which take care of most of the vulnerabilities, and also modular in such a way that can be upgraded in the future, either through software or with minimum hardware extensions and all. So this is exactly the problem of existing security. The future solutions might use PUF, physical unclonable functions, for the key generation and digital rights management. This is where exactly the PUFs can play a major role. Physical unclonable functions can play a major role. I think this ends my presentation. And again, you can write back to me. I think I have summarized this. One scalable infrastructure IP for security, which addresses all vulnerabilities for IoT, both at the hardware level and the software level, must be developed. And again, it's an open research problem always. Means even today, 3 years back, it was an open research problem. Even today, it's an open research problem. There is an incremental improvements here and there. We can see good papers in conferences and journals in this direction. But either they will address the network layer and application layer security problems, which is really not low power and which is not really commercially viable solutions. The people who are interested in research, both in industry and academics, can look into developing a scalable, holistic infrastructure IP for security, which is also addresses all security vulnerabilities of IoT with low power perspective. Is a very big open research problem. At least we can get very good research problems, very good PhD problems in this direction. So we have to read a lot of literature to find. to answer the questions. And fine, thank you.
Sir, thank you very much, sir.
Thank you, sir. Thank you very much.
Yeah, 1 minute, sir. Yes, sir. Thanks a lot for your very informative session, and really we are very much thankful to you.
Thank you, sir.
Yeah. In YouTube chat box also, we seen a few messages related to you saying they are expressing their what is that happiness while seeing you in YouTube during this session and after getting your informative session. Thank you very much, sir.
Thank you,
Just
sir.
I'm-
Thank you very much for
just
giving
I'm-
an opportunity.
Yeah. Sir, few questions are there. Only two questions
Please, sir.
are there. Ashok asked this question. Sir, what is the impact of Arduino in IoT in terms of power consumption?
Arduino is not power optimized actually. To see most of the low-end applications, especially when it comes to the home automation and all, there is no much problem using the Arduino there because the reliability and power consumption are not the primary goals when it comes to the home automation. But if it is Arduino is used in some applications like smart city, and there will be a serious battery problems across. We can read some literature, both commercial literature and also our IEEE journals that Arduino is not optimized for low power, especially when it comes to a large scale applications like smart city. In that place, we can choose any other, frankly speaking, there are a lot of other commercial solutions. To the best of my knowledge, there is some Intel microcontroller which fits the smart city application. Like that, we have to choose. If we are an hardware designer, pure play IoT solution provider, then we have to choose for a given application how much for how long batteries, how frequently we can replace the batteries of these nodes depending upon. But as of Arduino is concerned, it's good for home automation. When it comes to a large scale, it really not much good. No, not very good. I don't know about in last 2 years what are the development. At least last 1 year, what is the development? I am not aware. At least 1 year back, Arduinos were not good. Other like Intel were doing well. Yeah.
Sir, this is the last question from Srinivas Rao.
Sir.
What are the open source softwares available? Can you mention some?
The open source softwares are basically for what is the purpose, sir? What exactly you are looking for? I don't know. IoT is a very large ecosystem. There is a lot of things like testing, development, software development, hardware development, PCB development. Means in which area they are looking for a open source software must be listed here.
Sir, another question from Kalamani C. What are different low power techniques in IoT? I think it.
Yes, sir. One is the low power technique is low power software development. Only thing is, whatever we are doing, we have to minimize the switching activity in the similarly like how we do it in VLSI, minimizing the switching activity. We have to minimize the switching activity in the software also. Low power software, one particular application, one particular thing is switching off the network whenever it is not required. Then switching off the networks, switching off the modules which are not used. For example, ADC device driver can be enabled only when ADC is used. Means something like that controlling. Basically, we need a one FSM which controls the complete process. That depends upon application to application. I think a better literatures can be available for a given application. A generic low power software development theory is available, but practically it can be achieved only through some customization.
Yeah. Sir, this is the last question
Sir.
from the same participant, Kalamani.
Sir. Sir.
What are the open source softwares related to the hardware security kind of stuff?
Hardware security softwares means they can look into
Like
the
simulators.
website Trust Hub. They can look into the website called as a Trust Hub. There they have used. There is a lot of tools available, different purposes. Starting from Verilog development to starting from security checking, Verilog security checking, embedded software security verification. There is a list of softwares listed in the Trust Hub website. A participant can look into the Trust Hub website for more details on open source solutions for hardware security. Overall hardware security, which is also applicable to IoTs.
Thank you, sir. Our HOD sir wants to say thanks to you.
Thank you very much. Thank you very much, and thanks for giving me an opportunity, sir. Thank you very much.
Hello. At the outset, on behalf of GMR Institute of Technology, I would like to express my sincere thanks to all the participants and also today's speaker, Mr. Sudhindra Kumar. Presently, he is associated with NIT Roorkela. Sir, your session was very interesting. Initially, you have started with embedded system and you have explained IoT and the basic differences, and slowly you are dived into the research topics in IoT and the hardware tools related to it, and also you have clarified all the queries for the participants. And I have seen that after going through the chat box also, I can say that confirmly all the participants enjoyed the session. Thank you very much for sparing your valuable time with us and sharing your knowledge along with all participants. Thank you very much, sir. And
thank you, sir. Thank you very much. Thanks for giving me the opportunity.
Thanks for
sharing much.
One minute.
Thank you, Sudhindra sir. Thank you. Thank you, participants. Yeah, thank you, participants, for your patient listening. Again, let us meet by 5:30 today. That is the last session. That session will be followed by the well of 5 minutes. Thank you very much.